Consider the following example, which is designed to practice the concepts that we have just developed. So consider a market in which there are 100 identical consumers, each of one with wealth WI equals to $2 of the M good. There is also one firm, and only one, that has a cost function with the following properties. There is a semi-fixed cost of $100, and the marginal cost is fixed at $1 per unit. Now, what we want to do here is characterize or plot the set of feasible symmetric allocations. Now, importantly, we're not going to characterize all feasible allocations, only those that are symmetric. What do we mean by symmetric? Every consumer consumes the same bundle, and every firm produces the same amount. Now, of course, since here there is only one firm, that part of the symmetry is trivial. Now, the first thing I want to do to solve this example is to remind you of what the technology of the firm looks like under these assumptions. So this is in the x-axis, the quantity Q of good X that the firms produce, and I'm going to plot here the total cost in dollars that it takes to produce it. Now, notice that the firm can produce nothing, in which case it has to pay nothing in total cost. So that point is in the production function. Because why? Because these are semi-fixed costs. They only have to be paid if there is some production, otherwise they don't. Now, if the firms want to begin producing, it has to pay these 100 initial units in semi-fixed cost. Notice that that point is empty because it is only the semi-fixed costs are only paid if actually there is some production. But after that, the marginal cost is constant and equal to 1 unit, so the firm can take 1 unit of good M and transform it into 1 unit of good X in a 1-to-1 basis. Now we're going to plot the set of feasible symmetric allocations. Now, the way I'm going to do that is by doing a two-dimensional plot like this that denotes on the x-axis the amount of good M that every consumer is going to consume. Remember, in a symmetric allocation, every consumer consumes the same amount. And in the y-axis, the amount of the good X that is going to consume. And then I'm going to plot in red all of the combinations of M and X that satisfy the definition of a feasible symmetric allocation. Now, let's begin doing that. Clearly, we can give an amount of consumption of 2 units of M and 0 units of 0. Let me call this point 2, 0. Because we can have the consumers just consume their wealth of good M and have nothing produced by the production technology of the firm. So that point 2, 0 is clearly in the feasible symmetric allocation. Then I claim that there is this open point 1, 0, and this line that goes like this with a slope of -1, so this is -1, 1, and that any point in this line, any combination of M and X in this line is also part of a feasible symmetric allocation. Let's see why. But let's start with this tiny point that is here right next to 1, 0, although it's not quite 1,0. What does it, is it feasible? Well, in order to produce a tiny bit of X, we need to pay the semi-fixed cost and then pay the amount of good M that it requires to produce it. But notice that the semi-fixed costs are 100, so that's equivalent of taking 1 unit of good M from each one of the consumers and then using the rest to produce the good X with a marginal cost of 1. That's why we can expand the whole line at a slope of -1. Now, let me conclude the example by making some remarks that I hope are useful. The first one, I want you to notice that at no point I had to specify the preferences of the consumer to be able to characterize a set of feasible symmetric allocations. Why? Because this is merely an accounting exercise of resources. Preferences have nothing to do with it. All I have to do is find combinations of symmetric allocations and levels of production associated with them that make sure that all of the feasibility constraints for a feasible symmetric allocation actually hold. Remark number 2, I want you to notice that also prices and profit maximization and utility maximization play no role in the characterization of the set of feasible symmetric allocations. Why? Again, because this is merely an accounting exercise that keeps track of how much I can give to consumers and how much production I have to exercise in order to be able to make that allocation to consumers feasible. Finally, I want to emphasize to you the connection between production and consumption in the example. I have not written down the specific equations from the definition of a feasible symmetric allocation to keep the example intuitive and simple. But implicitly, I have been using them in order to characterize this curve. And in particular, it is very important in order to characterize the set of feasible symmetric allocations to notice that as I change the level of consumption of X, for example, by going in this direction, that also entails that I have to use the production technology in ways that are feasible. So to see that, consider the following example. This point, which is 0, 1, that level of symmetric consumption is in the set of feasible symmetric allocations. But in order to do that, I have to use the production technology at a level in which allows me to produce 100 units of the good. And the question is, how much M does that take to produce 100 units of the good? Well, we need to pay the semi-fixed cost, that's 100, and then produce 100 units at a marginal cost of 1, that's another 100. That means that I have to use 200 units of M, which is exactly the total wealth that consumers of M had, which is why if they end up consuming per capita 1 unit of X, they cannot get any consumption of M at all. I hope that the tight connection between the allocations that I can give consumers and how I use the production technology to make or produce those consumption bundles is clear now.